Hello everyone. Today we're going to look at solving an applied max and min problem. And our objectives are going to be the basic problem solving strategy, and we'll look at an applied minimum example. So our basic problem solving strategy will be step one to understand the problem. We'll draw an appropriate picture and label all our relevant quantities. Most of these problems are going to be geometric in nature. Step 2, devise a plan. We need to find formulas for both the quantity being maximized or minimized, so the actual quantity, have it be cost or area or volume that we're trying to maximize, and then some sort of constraint on the problem. Without a constraint, usually the maximization problem wouldn't make any sense, but combining those two, we should be able to maximize and quite often both minimize the quantity at hand. Step 3, carry out your plan. As always, we're going to have to implement some sort of equation solving strategy. In this case, it's that we'll find the interval of possible values for our main variable, and then we're going to optimize our quantity over that interval. Usually find the critical point, test some endpoints if necessary. On step 4, look back. Let's interpret the solution in terms of the original problem. Does our answer make sense? As always, does it make sense? And number 2, does it seem reasonable in terms of the application? So let's look at our problem. A rectangular area of 3,200 square feet is to be fenced off. Two opposite sides will use fencing costing $1 per foot, while the remaining sides require a more durable fencing that costs $2 per foot. Let's find the dimensions of the rectangle of least cost. So let's draw a picture. We have a rectangle, and we know that the area of the rectangle is 3,200 square feet. And we know that we're going to use different fencing on different sides. So maybe on this side, I have fencing that I'll call X. And on this side, I'll have fencing that I call Y. And since X is a shorter side, that's the side we'll probably use the $2 per square foot fencing, and then the $1 per square foot fencing there. So if we look, we want to try and minimize our costs. And so our cost is going to be the following. We will have paid $2 per square foot for 2x feet of fencing, because there are two sides with length x, and we will pay $1 per square foot with 2y feet of fencing, because there's two sides with length y. So this simplifies to 4x plus 2y. Now we need a constraint because this is a function of two variables. But our constraint is that it has to be an area of 32 square feet. So our area has to be 3,200 square feet. But we know that the area is going to be x times y. From the picture. Now we just make the substitution. We solve for y, that y is 3,200 over x. And then we simplify. So taking our cost expression from the last page and simplifying here, we get that the cost function is 4x plus 6,400 over x. Now we'll just differentiate the cost with respect to x. That gives us 4 minus 6,400 over x squared using our power rule. And then we're going to take that and we're going to set it equal to 0 to see if we can find any critical points. So if we go to solve for x, then we can get that 4 equals 6,400 over x squared, or that x squared is equal to 1,600. And so that x is just 40 feet. And we can then easily use the fact that y is equal to, if you remember our substitution, 3,200 over x. There's y right there. And that gives us 3,200 over 40, or 80 feet. So what are the dimensions of the rectangle of the least cost? The dimensions of the rectangle with the least cost will be 40 feet by 80 feet. And if you look, it does satisfy the fact that the area had to be 3,200 square feet. And it does seem reasonable that the cheaper side of fencing will be the longest. So that concludes our solving an applied max and min problem, and I hope you have a wonderful rest of your day.